Welcome to the session on Hebbian learning rule. The Hebbian learning rule, also known as Hebbs learning rule, was proposed by Donald O. Hebb and is one of the easiest learning rules in neural networks. It is used for pattern classification. It is a single-layer neural network with one input layer and one output layer. The input layer can have n number of units, while the output layer has only one unit. The Hebbian rule works by updating the weights between neurons in the neural network for each training sample. Hebb's principle can be described as a method of determining how to alter the weights between model neurons. When two neurons increases if the two neurons activate simultaneously and reduces if they activate separately. Nodes that tend to be either positive or both negative at the same time have strong positive weights, while those that tend to be opposite have strong negative weights. One of the key characteristics of Hebb's rule is that it doesn't need a teacher or a target label. It only looks for patterns and correlations in the data. In its simplest mathematical form, the change in weight between an input neuron and an output neuron is proportional to their simultaneous activation. Wi of nu is equal to Wi volt plus Xi y, where W is the weight, X is the input, and Y is the output. Update of weight and bias based on error is known as learning. The training algorithm of Hebb's rule is given as follows. Step 1. Set the initial weight to 0. Wi is equal to 0 for I is equal to 1 to n, where I is the total number of input neurons and the initial bias B is equal to 0. Step 2. Update the weight and bias. Wi nu is equal to Wi volt plus Xi y, where Xi is the input and Y is the output. B nu is equal to B volt plus Y. Change in weight is given by del Wi is equal to Xi y. Change in bias is given by del B equal to Y. Now we shall see a simple numerical to solve the given input sequence pattern using Hebb's rule. Calculate the new weights and bias by using the Hebb's rule to perform the following classification of the given input sequence pattern. Plus symbol represents a value 1 and the empty sequence indicates minus 1. Consider I belongs to a member of the class has a target value 1 and a O does not belong to the member of a class so has target value minus 1. The given sequence pattern for class I is plus 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 empty plus empty plus plus plus. Similarly, for class O, the given sequence pattern is plus 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 empty plus 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 plus. So it is stated in our numerical that the plus symbol is represented by the value 1. So all the plus we can represent it by giving a value 1 and the empty sequence we have to denote it as minus 1. Now we shall generate the input data for the given sequence pattern I and O. So input vector for class I is given as I is equal to 1, 1, 1, minus 1, 1, minus 1, 1, 1, 1. Similarly, the input vector for class O can be given as 1, 1, 1, 1, minus 1, 1, 1, 1, 1. The target for class I is given as 1 and target for class O is given as minus 1. Now, the input sequence pattern as per the numerical has 9 values. So, it can be represented from x1 to x9 and the target can be represented by y. There are two classes I and O. We have represented the data values for the given input sequence pattern for class I and class O. Class I, the data is plus 1, 1, 1, minus 1, 1, minus 1, 1, 1, 1. Similarly, class O, the data is 1, 1, 1, 1, minus 1, 1, 1, 1, 1. The target for class I is plus 1 and the target for class O is minus 1. So as per our Hebbs rule, the initial weight is assumed to be 0. So the initial weight is given as 0. Now we shall determine the change in weight for class I. So change in weight, the formula is xi into y. So x1 into y will be del w1. Similarly, x2 into y will be del w2. x3 into y will be del w3. x4 into y will be del w4. x5 into y will be del w5, etc. So del w1 is x1. x1 is 1 into y is 1. So 1 into 1 is 1. Similarly, 1 into 1 is 1. Similarly, minus 1 del w4 minus 1 into 1 is minus 1. So similarly, we have calculated the change in weight for class I as 1, 1, 1, minus 1, 1, minus 1, 1, 1, 1. Now we shall determine the updated weight for class I, which is given by Wy new is equal to Wy old plus Xi y. So Wy old, that is the initial weight, which is 0, and the change in weight is given by del Wi. So we have to add the values present in this row and present in this row to determine the updated weight Wi new. So 0 plus 1 gives us 1. Similarly, 0 plus 1, 1. 0 plus 1, 1. 0 plus minus 1, minus 1. 0 plus 1, 1. 0 plus minus 1, minus 1. 0 plus 1, 1. 0 plus 1, 1. 0 plus 1, 1. And this is the updated weight for class I. Now we shall determine the change in weight for class O, which is given by the same formula x1y, x2y, etc. up to x9y. Now x1 is 1, y is this one. So 1 into minus 1 gives us minus 1. 1 into minus 1 gives us minus 1. 1 into minus 1 gives us minus 1. 1 into minus 1, again minus 1. Minus into minus 1, which is 1. 1 into minus 1, minus 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 1. This is the change in weight for class O. Now we have to calculate the updated weight for class O. So for updated weight for class O calculation, we have to use the Wi old as the updated weight of class I. So summation of these row values and these row values is going to give us the updated weight for class O. So 1 plus of minus 1 is 0, 1 plus of minus 1 is 0, 1 plus of minus 1 is 0, minus 1 plus of minus 1 is minus 2, 1 plus of 1 is 2, minus 1 plus of minus 1 is minus 2, 1 plus of minus 1 is 0, 1 plus of minus 1 is 0, and 1 plus of minus 1 is 0. This is the updated weight for class O. So now we have calculated the updated weight for the given input sequence patterns class I and class O. Hope you have understood this sum. Next example, we shall see how to update the weight and bias of a AND NOT logic gate using bipolar logic. So first we shall see the truth table of AND NOT logic. So the output expression for AND NOT logic is y is equal to x1 into x2 bar. So here we have considered two input AND gate. So there are two inputs x1 and x2. So input values or input combinations are 0, 0, 0, 1, 1, 0 and 1, 1. To determine the output expression, y is equal to x1 into x2 bar. x2 bar is 1. So 0 into 1, 0. Similarly, 0 into 1 bar, that is 0. So output is 0. 1 into 0 bar, that is 1. So 1 into 1 is 1, and 1 into 0, which gives us 0. So same can be converted in a bipolar form. In bipolar form, zeros are represented by -1. So the 0 here will be presented as -1. Similarly, the 0 is represented as -1. So the truth table is as follows. -1, -1, -1, -1, 1, -1, 1, -1, 1, 1, 1, -1. Now we shall see how to update the weight and bias using Hebbs logic for this truth table of the AND NOT logic in bias. Now we shall see how to solve the AND NOT logic using Hebbs rule. The truth table of the AND NOT logic is updated here x1, x2, y, and change in weight, change in bias, updated weight and updated bias is going to be calculated. So for the first input combination -1, -1, the target is -1. So del W1 is -1 into -1, that is 1. Del W2 is -1 into -1, 1. Del B is y is equal to -1. W1, the updated weight, is nothing but old weight plus change in weight. Old weight, initial weight is considered as 0. So our old weight will be 0. So 0 plus 1, that is 1. Similarly, W2, 0 plus del W2, that is 1. And bias is 0 plus -1, that is -1. For the second input combination, -1, 1, -1, del W1 is -1 into -1, that is 1, 1 into -1, that is -1, and V is -1. The new weight or the updated weight is 1 plus 1, that is 2, 1 plus -1, that is 0, -1 plus -1, that is -2. For the third input combination, 1, -1, the target is 1. So change in weight will be 1 into 1 is 1 for W1, and -1 into 1, -1 for del W2, and 1 for del B, that is the target. And the new weight W1 will be 2 plus 1, that is 3. W2 will be 0 plus -1, that is 0. And B will be -2 plus 1, that is -1. For the last input combination, 1, 1, the target is -1, and del W1 will be 1 into -1, that is -1. W2 will be 1 into -1, that is -1. And del B is nothing but y, that is -1. The new weight will be W1 is equal to 3, W1 old, that is 3, plus change in weight -1. So 3 plus of -1, which is 2, and W2 will be -1 plus of -1, that is -2, and updated bias will be -1 plus of -1, that is -2. So the updated weight for AND NOT logic is 2, -2, -2. So hope you would have enjoyed the session on Hebbs learning rule.